Mars has always been a little too good at lying to us. Through shaky telescopes, people once thought they saw dark lines carved into its surface and convinced themselves that engineers were pumping water across a dying world. Later spacecraft sent back the famous face in the rocks, and millions decided it had to be a monument. Then sharper cameras arrived, and those canals dissolved into noise, that face blurred into an ordinary hill, and the grand Martian civilization evaporated overnight. Yet the deeper question never left. Under all those tricks of light, did this planet ever truly live? Or have we been chasing ghosts across a desert the entire time? If you and I had lived a century ago, our answer would have depended almost entirely on the limits of glass and imagination. You pointed a telescope at the red dot in the sky, you sketched what you thought you saw, and the rest was storytelling. Today the game is very different. Now we drop robots out of screaming atmospheric fireballs, land them on ancient lake beds and floodplains, and ask them to read the rocks as if they were diaries written in minerals. We send orbiters to map clays and sulfates from above, landers to listen for the slow heartbeat of the core, and rovers to grind and drill into layers that have not seen daylight for billions of years. Mars still plays tricks on the eye, but it no longer gets to control what we know. For most of the 20th century, Mars lived in a kind of scientific limbo. Telescopes and the first flyby probes showed a cold, dry world with thin air and huge volcanoes, but they did not have the resolution to answer the questions that really mattered. Was there ever a deep ocean in the low northern plains? Did rivers once braid their way through canyons like Valles Marineris? How long did liquid water last on the surface before the atmosphere thinned and the temperature fell below the freezing point almost everywhere? Every new mission seemed to flip the story one way and then the other. One lander would find chemistry that looked strangely active, another would find soils that seemed oxidized and hostile to organics. Each result arrived like a fragment torn from a book whose pages had been scattered across the entire planet. That shift is really what our story is about. Not just whether Mars was ever habitable in some vague, poetic sense, but whether it once had long-lived lakes and shallow seas where something microbial could take hold and evolve. Not just whether the planet still trembles with hidden tectonic aches, but what that interior structure tells us about worlds that cool, stall, and lose their magnetic shields. And not just whether the surface is weird and beautiful, but whether those weird shapes are geology, scraps of our own machinery, or the first fossil that finally forces us to stop saying maybe. The red planet is no longer a blank canvas for speculation. It is a crime scene that 3 different missions have been patiently documenting for years. Think of Opportunity, the rover that was only supposed to last 90 Martian days, and instead wandered Meridiani Planum for nearly 15 years. Its entire job was to answer one question with brutal clarity. Did this patch of Mars once have liquid water for extended periods, or was it just splashed and dried like a parking lot after a storm? Then think of Insight, the lander that did not move at all, yet reached deeper into the planet than any rover wheel ever could by listening to Marsquakes and meteor impacts. Its question was even more basic. Is Mars truly dead inside? Or is there still motion and heat working slowly in the dark? And finally, think of Perseverance, the most ambitious rover yet, sent to an ancient river delta in Jezero Crater to collect rock cores that could one day be flown back to Earth and inspected for actual fossils. It carries cameras that can see textures at the scale of grains of sand, lasers that can read chemistry from a distance, and a sample caching system designed like a tiny time capsule factory. Every tube it seals is meant to be a potential answer to the question that every other mission has been orbiting. Did life ever start here? In other words, these 3 machines are not isolated projects. They are chapters in a single investigation into whether Mars was once a living world or has always been only a stage set. These machines did not arrive on a blank slate. Long before Opportunity rolled off its landing platform, scientists were already building layer upon layer of expectation. Orbiters had mapped strange blue-tinted patches that hinted at minerals formed in water. Earlier landers had tasted soils that seemed oddly rich in chemistry, yet stubbornly refused to prove biology. Radar had hinted at buried ice, and thermal maps had suggested volcanic regions that might still smoulder far below. By the time a new mission was launched, it was walking into a web of hypotheses as tangled as the old Canal stories, only this time backed by spectra and models rather than pencil sketches. Our story has to untangle that web, because every surprising rock and every faint tremor makes sense only in the context of what scientists expected to find. When a rover sees layered sediments, the question is not only what they look like, but whether they match the climate models that predicted shallow seas or episodic floods. When a lander feels the planet shiver, the question is not just how strong the quake was, but whether it fits the idea of a cooling core and a thick, rigid crust. As we walk through this evidence, it helps to keep asking yourself what scientists thought Mars would be before the data arrived, and how each new measurement forced them to redraw the picture. And then there is the human brain, which might be the most unreliable instrument we have ever sent to Mars. When Perseverance started sending back its first high-resolution panoramas, the internet immediately lit up with zoomed-in crops of rocks that looked like cats, fish, doors, even snakes frozen mid-slither. People circled them in red and shared them as proof that something unnatural had to be going on. The same thing happened decades earlier with the so-called Face on Mars, that hill in the region of Cydonia that looked uncannily like a carved human head in early images, and then melted into meaninglessness when seen with better cameras. The same pattern plays out over and over. Our minds are built to find faces in clouds and creatures in shadows, and Mars is a wilderness of jagged shadows. Give a human a noisy image and a little context, and the brain will gladly supply eyes, mouths, tunnels, even machines. That ability to see patterns where none exist is part of what kept our ancestors alive in dangerous environments, but it is a nightmare when you are trying to honestly interpret alien geology. If we are going to be serious about the search for life, we have to start by admitting how easily we fool ourselves. This is why robots are such good partners in this investigation. A rover does not get excited about a rock that looks like a skull. It does not feel creeped out by a lonely boulder sitting on an otherwise flat plane. It simply compares shapes, measures spectra, checks how easily the drills bite, and quietly sends numbers back home. But those machines are not truly neutral either, because every sensor they carry is the physical imprint of a human question. Opportunity carried instruments tuned to iron-rich spheres and sulfate-rich layers, because scientists already suspected that Meridiani Planum had once been soaked in salty groundwater. It had a microscopic imager to peer into the texture of rocks and a tool to grind away dusty coatings, all because the team believed that the story of water was written there in fine detail. InSight carried a hammering heat probe because we desperately wanted to measure how fast the interior was cooling and whether there was still convection deep down that might someday restart a magnetic field. Perseverance carries that complex sample caching system because we finally accepted that the ultimate proof of life will not come from a camera frame that looks odd. It will come from cores studied for years under microscopes on Earth. So as we follow these missions, we are not just watching machines trundle across a distant desert, we are watching an idea evolve. The idea starts with a gaze through an eyepiece and a hope that canals mean cities. It passes through the disappointment of barren landscapes and the thriller-like tension of risky landings. It grows more sober as data piles up, showing oceans lost, air stripped, interiors cooled and locked. And yet, underneath that sobering story is a much more hopeful one. If Mars once had thick air, flowing water, active volcanoes, and a global magnetic shield, then the early solar system may have been packed with habitable worlds. If Mars lost all that and still kept clues tucked away in its rocks and crust, then those clues might exist on many other planets and moons as well. In that sense, this is not only a story about a single cold world, it is a rehearsal for how we will read the histories of 1,000 other planets we have not yet seen up close. You and I live at a very particular moment in that evolving idea. Opportunity has already gone silent, caught in a planet-wide dust storm that smothered its solar panels and plunged it into a night it never woke from. InSight, after years of listening to the planet shudder, has powered down as dust slowly choked its own arrays.
Perseverance is still rolling and drilling as you hear this, storing pencil-thin cores of rock that may one day be the most valuable stones humanity has ever held. For the first time, we have a full arc of evidence that stretches from the chemistry of ancient water to the rumble of modern Marsquakes, and from the textures of sedimentary layers to the razor-carved edges of once molten lava. The question that haunted those early Canal observers is finally being tested in a way they could never have imagined. The challenge for us is to follow that evidence without losing the sense of wonder that drew people to Mars in the first place. When you hear that Opportunity found blueberry-like hematite spheres, it is tempting to let the technical name slide past and wait for the headline moment. When you hear that InSight used the travel time of seismic waves to sketch the size of the core, it can sound like abstract homework rather than a revelation. When you hear that Perseverance has successfully sealed another sample tube on Jezero crater's floor, it might feel routine. Yet each of those things chips away at the same mystery. Was Mars ever a living world, even at the level of microbes, or has it always been a grand stage with no actors? So here is what we're going to do together.
We will walk alongside these missions, from Opportunity's first bounce in Eagle Crater to its last dark horizon, from InSight's fiery descent to its final whisper of power, and from Perseverance's sky crane ballet to the moment its drills first bit into Martian rock. We will slow down just enough to understand what each measurement really meant, without drowning in formulas, and we will keep asking one question at every step. Does this bring us closer to a clear yes or no about life, or does it deepen the maybe? By the time we reach the end of that path, you might find that the most shocking thing about Mars is not a strange rock or a dramatic storm, but what this quiet, cold planet is really telling us about how fragile and how common life might be in the universe.
To see how a quiet desert world started to confess its past, we have to drop with Opportunity into a night of fire. The rover arrived at Mars in early 2004, packed inside a protective shell that slammed into the atmosphere at hypersonic speed. Friction heated the air until it glowed. Then a parachute opened and airbags inflated, turning a small robot into a bouncing ball the size of a car. It hit the ground, bounced, rolled, bounced again, then finally came to rest inside a crater, only a few tens of meters across. Engineers on Earth did not yet know that this tiny bowl, later named Eagle Crater, was the best possible accident. It was as if someone had gently placed a field geologist right in the middle of an exposed road cut. Opportunity was the younger of two twins.
Its sibling, Spirit, had gone to a volcanic plain on the other side of Mars to study ancient lava flows and possible past hot springs. Opportunity was targeted at a different mystery. From orbit, an earlier spacecraft had mapped this region, Meridiani Planum, and spotted a strange signal from iron-rich hematite. On Earth, that mineral often forms in water. If you wanted to test whether Mars had once been wet for a long time, this was where you would send a rover. The plan was modest. Drive a little, look around, operate for about 90 Martian days, and then fade as dust and cold took their toll. The morning after landing, as sunlight reached its solar panels, Opportunity woke up and slowly unfolded itself. Petals of the landing platform opened.
The rover raised its mast and began to turn its cameras. When the first panoramic images trickled back to Earth, the room at Mission Control went very quiet. Instead of a flat plain of soil and scattered rocks, the rover saw layered bedrock exposed in the walls of the small crater, all around it in a gentle ring. You can imagine standing there in person, looking up at those layers and feeling that this was not random rubble. It looked like pages of a storybook that had been sliced open for reading. The science team knew that this was already a jackpot. On most of Mars, rocks are buried under dust and broken fragments. Bedrock that still sits in place, showing fine layering and texture, tells you about the environment right where it formed, not about some distant source.
Opportunity crawled down off its platform, rolled onto the soil, and began a slow, careful inspection of the crater wall. The rover had a turret at the end of its arm, a kind of Swiss Army knife that could brush dust away, press instruments against rock, and take close-up pictures sharp enough to show grains of sand and tiny crystals. Each move was planned days in advance. Each contact with a rock was a small, deliberate experiment. Very quickly, one feature jumped out. Scattered across the soil and embedded in the rock were tiny, round pellets of hematite. They were only a few millimeters across, but in the images they stood out as dark, spherical beads. On Earth, similar structures are often called concretions.
They grow when mineral-rich water flows through porous rock and slowly precipitates material around a central seed, layer by layer. That suggested something profound. Whatever had happened here was not a single flash flood. It was a long process with groundwater moving through the subsurface, changing chemistry over time. At the same time, the layering in the rock told its own story. In some places, the layers were flat and thin, stacked like delicate sheets. In others, they showed cross-bedding, tiny angled structures that you also see in sand ripples under shallow water or in dunes shaped by wind. Opportunity took stereo images that let scientists reconstruct the slopes and directions of these mini-layers.
Put together, they painted a picture of a landscape that had seen both wind and water, shifting back and forth over periods far longer than a single storm. This was not a simple story of an occasional wetting. It hinted at an environment that stayed active and changing for a long while. Chemistry backed that up. Using its spectrometers, Opportunity measured the elements present in different layers and in the little hematite spheres. It found that the rocks in Eagle Crater were rich in sulfur and other elements that often show up in evaporite deposits, which are rocks left behind when salty water evaporates. There were also minerals such as jarosite that tend to form in acidic water.
So Meridiani Planum, at least in this patch, seemed to have once held shallow, salty, and acidic pools or groundwater. That was not the gentle, neutral ocean that people once imagined when they drew blue seas over maps of Mars. It was more like a harsh, briny marsh on a bad day. On Earth, acidic, salty environments are not the end of the story for life. They are the starting point for some of the most stubborn microbes we know. There are bacteria that thrive in acidic mine drainage, and others that live in brine pockets in sea ice. So while the conditions Opportunity was uncovering were tough, they were not impossible. If anything, they made Mars more interesting. We were not looking at a cozy twin of Earth.
We were looking at a world that might have had extreme habitats, the sort of places where life has to work hard to hang on. That is exactly where you want to look if you are trying to understand how flexible life can be. All of this came from a single, small crater near the landing site. That raised an obvious question. Was Opportunity seeing something local and unusual, or a glimpse of a more widespread environment? To find out, the rover had to leave the comfort of Eagle Crater and roll out onto the surrounding plain. That meant climbing a short slope of loose material and trusting that its 6 wheels would not slip or sink. Controllers back on Earth simulated the climb using a twin rover in a sandy test yard, tweaking wheel speeds and approach angles until they were confident. Then they sent the commands and waited for the next batch of telemetry to arrive. Opportunity made the climb without trouble. It drove up the inner wall, reached the lip, and emerged onto a landscape that suddenly looked much more like the Mars many had expected. The horizon was almost flat. A dusty plain stretched away, with scattered rocks and small ripples, under a thin, salmon-coloured sky. But here and there, in the distance, the rover could see darker circles. These were other craters, some larger, some smaller, each promising another chance to cut down into the layered rocks. The mission shifted from careful work inside one crater to a slow campaign across the plain, hopping from exposure to exposure. As it drove, the rover kept finding the same overall pattern.
Rock showed the familiar little hematite spheres and the sulfur-rich chemistry. The plain was not just a random patch of wetness. It seemed to be the surface expression of a broad deposit of sediments, laid down in a watery or water-influenced environment. That alone would have made the mission a success. The space agency could have declared victory and quietly accepted that the rover would die when winter arrived. Instead, the team looked at a larger, more dramatic target on the horizon and asked a harder question. What if we go there and risk everything to see deeper into the past? That target was Endurance Crater. Compared to Eagle, it was a giant. Its floor lay tens of meters below the surrounding plain.
From orbit, it showed thick stacks of layered rock exposed in its walls, like a natural core sample. From the rim, Opportunity could see those layers in more detail, bands of lighter and darker material repeating down to the shadowed interior. The scientific temptation was obvious. Each layer was a snapshot of a different time and set of conditions. If the rover could work its way down safely, it might be able to read a vertical history of changing water levels, changing chemistry, and changing climate. The risk was equally obvious. Driving into Endurance meant committing the rover to slopes steeper than anything it had faced before. If its wheels slipped too much on the dusty, loose material, it might slide or get stuck. Climbing back out would be much harder than driving in. Engineers ran scenario after scenario. They used test rigs to mimic the angle and soil properties. They measured how the rover performed when it was tilted, how much energy it consumed, how its instruments behaved. Some argued that the rover was too valuable to risk. Others argued that its very value came from taking these carefully calculated risks. In the end, curiosity won. The team plotted a path that would take Opportunity down along a relatively gentle section of the wall, in stages, stopping often to check traction and reassess. Each descent move was followed by a pause to test whether the rover could back up even a short distance. Only when they were confident that it still had a path home did they send it onward.
This cautious, stepwise approach turned the descent into a series of experiments. The rover was not only reading the rocks, it was testing the terrain itself, one short slide at a time. As Opportunity moved down into Endurance, the rocks around it changed. At the upper levels, the layers looked similar to those near the surface, rich in sulfates and hematite, with cross-bedding and ripple marks. Lower down, the patterns shifted. Some layers were more finely laminated, suggesting quieter water. Others showed thicker, more massive textures, perhaps deposited during more energetic events. Tiny cavities called vugs appeared, small holes where crystals had once grown and then dissolved away.
On Earth, such features often form when minerals precipitate in wet environments and later get removed, leaving empty spaces. The deeper the rover went, the more it became clear that Meridiani Planum had not experienced just one type of watery environment. There had been cycles, periods when water or groundwater was more abundant, and periods when it retreated, times when evaporation and mineral deposition dominated, and times when winds shaped the surface. The stack of layers in Endurance recorded shifts in climate and hydrology over what was likely a long stretch of Martian history. Opportunity was not just showing that water had been there, it was showing that water had come and gone, reshaping the same region again and again. For the search for life, that matters.
Microbes do not just need water once. They need it to persist long enough for ecosystems to establish and adapt. Repeated wet and dry cycles can concentrate chemicals, drive reactions, and create a variety of niches. On Earth, some of the richest microbial communities live in environments that flood and dry out on a regular basis. So when you hear that a rover has found evidence for multiple episodes of wetting and drying in Martian rocks, it is not a dry detail. It is a hint that the stage for life, if it ever took the opportunity, was reset many times, perhaps giving it more chances rather than fewer. At the same time, the chemistry Opportunity uncovered suggested that any ancient life here would have had to tolerate stress.
High acidity, high salinity, and oxidizing conditions are not friendly to fragile cells. That does not make life impossible. It shapes the kind of life you expect. On Earth, acid-loving and salt-loving microbes build biofilms on rocks, hide in pores, and form mats in shallow pools that can look almost like paint. If you let your imagination run a little, you can picture similar communities clinging to grains in Meridiani sediments long ago, leaving behind textures or chemical traces so subtle that only a rover inches from the surface could ever hope to detect them. By the time Opportunity had finished its work in Endurance Crater, It had far surpassed its planned lifetime.
The rover had endured dust storms, sharp cold, and the gradual wear and tear of repeated arm movements and wheel turns. Its flash memory began to show glitches. Its joints creaked a little more in telemetry data. Yet the core question that had sent it there had shifted rather than disappeared. At first, the mission asked whether Meridiani Planum had ever experienced long-lived water at all. The answer was a clear yes. Now the question was more nuanced. How widespread were these environments, and how did they fit into the larger story of Mars losing its atmosphere and its warmth? Standing virtually with the rover on the rim of Endurance again, looking out over the plain, you can feel that the mission is at a pivot point. Close work in nearby craters had revealed a rich local history. The next step would be to step back, treat Meridiani as a chapter, and ask how it connects to deeper, older terrains on the horizon. Far away, the rim of a much larger crater called Victoria cut a faint arc against the sky. Beyond that, even farther, lay the barely visible hint of an ancient impact basin named Endeavour. For a machine that had been designed to explore for 3 months, those distant rims might as well have been another planet. And yet, somewhere in that direction, the next set of clues about Mars and its long, slow transformation were already waiting. From the rim of Endurance, the horizon looked almost empty. A thin sky, a faint sun, and a line where ground met clouds of dust in the far distance. Yet for the team on Earth, that view was charged with ambition.
Somewhere out there was a much larger crater named Victoria, a bite taken out of the plains that might show an even deeper slice of history. Beyond that, farther than anyone had dared to plan for a 3-month rover, lay the ancient rim of Endeavour, a relic from a much earlier chapter in Martian time. Turning that distant promise into real tracks meant accepting that Opportunity was no longer a short mission. It had already outlived its warranty many times over. Now it would have to become something new, a long-distance explorer crawling across a foreign continent. This was not a simple matter of pointing it toward a target and hitting go. Every drive had to respect power limits, wheel slip, navigation hazards, and the fatigue slowly creeping into hardware that had already survived more Martian winters than expected. The plain of Meridiani Planum looks flat from orbit, but up close it is textured and subtle. Small ripples of sand run in parallel, carved by thin winds over long spans of time. Scattered rocks punctuate the surface, some half buried, others perched as if dropped from the sky. Between them, patches of bedrock break through the soil like eroded pavement. For a rover, that mix is both an opportunity and a trap. Hard rock gives secure traction. Loose ripples can grab a wheel and hold it. Earlier in the mission, Opportunity had already had a scare. While crossing what looked like a harmless stretch of light-toned soil, its wheels had broken through a crust and sunk deeper than anyone liked. The rover spun, dug in, and barely moved forward. Engineers watched as wheel currents spiked and the vehicle threatened to bog down. That place was later nicknamed Purgatory Dune. It was a harsh reminder that on Mars, what looks like a firm path can be a powder-filled pit that swallows you slowly, centimetre by centimetre. After that near trap, the team changed how they drove. They studied ripples and dune faces more carefully, choosing paths that kept the rover on rockier ground whenever possible. They limited daily drive distances, checked for slip after even modest moves, and used images from orbit to flag dangerous terrain in advance.
Opportunity also benefited from something no one had dared count on. The same winds that built the ripples sometimes swept dust off its solar panels. These cleaning events could boost its power by dozens of % in a single day, buying more margin for travel and science. Life as a long-distance rover settled into a rhythm. In the Martian morning, as the sun rose and panels warmed, electronics came alive. Opportunity ran health checks, calibrated instruments, and then crept forward along a planned path. It would stop, take images with its navigation and panoramic cameras, sometimes examine a rock in more detail, then sleep again to recharge.
Back on Earth, teams of scientists and engineers would pore over the new data, adjust the route, pick targets, and write a fresh sequence of commands. The rover and its human partners moved together in a slow dance set to the planet's day. Weeks turned into months. The crater Victoria grew from a faint smudge on the horizon into a distinct feature. From orbit, it was roughly 800 meters across, a deep, circular wound in the plains with a scalloped rim and steep walls. From ground level, as Opportunity drew nearer, it resolved into cliffs and promontories, with bays where the rim had collapsed inward and capes where erosion had left harder rock standing. For a geologist, this was irresistible. Each cape was a chance to see layers that had been buried under the plains, now exposed by the violence of impact and erosion. Reaching the rim of Victoria felt almost like arriving at a coastline. Opportunity could look down into a hollow that extended far below its wheels, with the plain behind it and the far rim forming a distant shoreline. The walls were decorated with bright layers and darker bands, carved and undercut by eons of wind. The mission team gave local names to these features, capes and bays that would serve as reference points for both images and plans. Once again, the same question arose that had haunted the descent into Endurance. Do we dare go in? The slopes into Victoria were steeper, and the interior was filled with deep drifts of sand.
A simple slide could bury a wheel so deeply that no amount of clever driving would free it. So the team began by scouting the rim. Opportunity drove around, stopping at each cape to take high-resolution panoramas and examine the layering. These images showed that the same sulfate-rich sediments found elsewhere extended down into the crater walls. The deposit was thick, a persistent chapter in the history of Meridiani. That alone made the long drive worthwhile. Still, the temptation to dip inside was too strong to ignore. After months of planning, the team chose a point where the slope seemed manageable and the underlying rock looked firm. They commanded Opportunity to venture down just far enough to touch and examine the walls at close range, then tested whether it could climb back out.
The rover performed with its usual quiet persistence. It drove down, deployed its instruments, and then patiently clawed its way back up, inch by inch. Each successful climb boosted confidence and allowed a slightly deeper foray, but the team never forgot that a single misstep could strand the rover forever. Inside Victoria, the story in the rocks gained depth. Opportunity saw subtle changes in texture and composition as it sampled different layers. Some horizons held more resistant nodules, others crumbled more easily under the grinder. These variations suggested shifts in water chemistry and environmental conditions over time. The crater was not just a hole in the ground, it was a vertical timeline, a record of how Meridiani's watery era evolved and faded.
The more clearly those layers spoke, the more obvious it became that the story they told was part of something larger. That larger story lay in terrain that was older than the sulfates themselves. From orbit, spectral instruments had mapped small patches near the rim of Endeavour Crater where clay minerals seemed to exist. Clays, or phyllosilicates, usually form in more neutral water, less acidic and more gentle on complex organic molecules. If the Meridiani sulfates represented a later, harsher phase of Mars' wet history, the clay-bearing rocks at Endeavour might preserve an earlier, more hospitable time. The idea of reaching them was bold. Endeavour was more than 10 kilometres away when the plan first took shape. To most machines, 10 kilometres on Mars would be impossible. To Opportunity, with years already behind it and unknown years ahead, it became a goal worth chasing. After Victoria, the mission team made a decision that would redefine the rover's legacy. They would treat Meridiani's sulfates as surveyed, accept that the most accessible slices of that deposit had been red, and aim the rover toward Endeavour's distant rim. This was not a sprint. It would be a trek lasting several Earth years, crossing terrain no one had explored before, driven by a machine that was already old by space standards. As the rover set off, new challenges emerged. Mechanical joints had endured thousands of actuations. One steering actuator on the front wheel had already failed, locking that wheel in a fixed position.
The team adapted, driving with limited steering and planning paths that minimise stress on the damaged joint. Memory glitches in flash storage meant that the rover sometimes forgot recent commands or data. Engineers developed workarounds, including operating in ways that relied more heavily on volatile memory that cleared at each sleep cycle. Every solution was a patch sewn onto an aging but still sturdy suit. Along the way, Mars continued to offer the unexpected. On one occasion, controllers noticed a rock that appeared in front of the rover between one set of images and the next. It was a small white-rimmed object, shaped roughly like a jelly donut, that had not been there before. For a brief moment, speculation flared. Had something strange happened? The more prosaic answer soon emerged. The rock, which the team nicknamed Pinnacle Island, had likely been flipped by one of the wheels, exposing a fresh interior. Its composition turned out to be unusual, rich in certain elements, but entirely explainable within the local geology. Still, the episode was a gentle reminder of how eager we are to see anomalies as mysteries before we see them as mechanics. Another cosmic visitor made the Martian sky itself into a spectacle. A comet called Siding Spring swept unusually close to Mars, passing near enough that its tail of dust posed a small but real risk to orbiters and surface assets. To protect the spacecraft, controllers maneuvered orbiters to shelter behind the planet during the peak of the encounter and adjusted the timing of certain activities. Opportunity, hunkered on the ground, was an unblinking witness to a rare event. While it did not capture dramatic images of the comet streaking by, the coordinated dance of machines around Mars showed how even distant icy bodies can change the operational rhythm of a mission. As the years passed, the rover's odometer ticked upward. It eventually passed the distance record set by human-driven lunar rovers, becoming the most travelled off-world vehicle in history. Yet those numbers were almost incidental to the science. Inch by inch, Opportunity approached the uplifted rim segments of Endeavour, small rises on the horizon that slowly grew into distinct hills. When it finally reached a section called Cape York on the crater's western rim, the ground beneath its wheels changed. The familiar sulfate-rich plains gave way to older, more ancient-looking rocks. At Cape York and nearby sites, Opportunity found outcrops that matched the orbital hints of clay minerals. One target, later named Esperance, showed evidence of alteration by water that had not been as acidic as Meridiani's later brines. The chemistry pointed to an environment where liquid water percolated through fractures, altering the rock in ways that would have been far friendlier to delicate organic structures. In the layered past of Mars, this seemed to be an earlier chapter, one in which the planet's surface water was less harsh and perhaps more suited for the emergence of life. For scientists, this was a crucial pivot. Up to this point, Meridiani had painted a picture of a wet but stressful world. With the clay-bearing rocks at Endeavour, a complementary picture emerged of a time when conditions may have been more moderate. Life, if it ever began on Mars, would have had a broader menu of environments to choose from. It could have found refuge in neutral water within fractures, even as larger surface basins shifted toward more acidic states. That diversity of habitats is exactly what you would hope to see on a planet where biology has a chance to start and adapt. Opportunity continued to explore segments of Endeavour's rim, rolling along its fractured, uplifted edges and stopping to examine promising veins and outcrops. It found bright mineral veins rich in calcium sulfate, likely left behind by water moving through cracks. It found textures in rocks that suggested they had been fractured, altered, and cemented over long spans of time. Each new observation fit into a growing understanding of Mars as a planet that did not simply go from wet to dry in a single step, but passed through a complex sequence of shifting conditions. All the while, the environment pressed in. Dust slowly accumulated on the rover's solar panels, dimming their output. Cleaning events still occurred, but they were not guaranteed. Winters at these higher southern latitudes brought lower sun angles and colder temperatures, forcing the team to park the rover on north-facing slopes to maximize sunlight. Opportunity spent some seasons tilted like a camper on a hillside, conserving power and doing limited work until conditions improved. Every winter survived felt like borrowed time. By 2018, the rover had been on Mars for more than 14 years. Its wheels were worn, but still turned. Its instruments were old, but still returned valuable data. Engineers had learned to live with its quirks, including the decision to disable its unreliable flash memory and operate in a mode where data had to be sent home each day or lost. This made Opportunity more vulnerable to communication gaps, yet it kept working. The machine had become a kind of elder in the fleet of Mars explorers, still productive, still revealing details about rocks and soils that no other mission could match. Then the sky began to darken. It started with reports from orbiters of a regional dust storm growing in the southern hemisphere. Such storms are common. They can cover large areas and then fade. But this one did not fade. It strengthened, expanded, and began to wrap itself around the planet. Fine dust rose high into the atmosphere, turning the sky from pale blue to brown to a deep, choking orange. For a rover that lived on sunlight, this was trouble. The amount of light reaching Opportunity's panels dropped sharply. Power levels fell, cutting into the energy available for heating and communication. The team watched the numbers with mounting concern. They had experienced storms before, but never one that cut so deeply into the energy budget. At some point, there is a threshold where a rover cannot keep its batteries warm and run its radio at the same time. To survive, it must enter a low-power fault mode, shutting down almost everything and waiting for the sun to return. Opportunity crossed that threshold in June. It sent a final transmission that indicated extreme darkness and low power, then fell silent. From its perspective, it was simply executing the logic it was built with, going to sleep to ride out a harsh spell of weather. On Earth, the silence was anything but routine. Days passed, then weeks, then months. Engineers sent wake-up calls, scanned the frequencies, and watched for any sign that the rover had reawakened. At the same time, they tracked the evolution of the dust storm, which gradually thinned and cleared. Orbiters saw the surface again. The sun returned to something like normal brightness. If Opportunity had survived the cold and the long blackout, it might have heard the calls and tried to answer. It did not. In the end, the most likely story is simple and harsh. The prolonged darkness and reduced power allowed the rover's internal temperature to drop below the safe range. Batteries and electronics built for a certain level of cold were pushed beyond it. Some component essential to waking up and talking failed quietly in the night. The machine that had walked Mars for nearly a decade and a half remained there, intact but unresponsive, a silent monument sitting on the slopes of Endeavour's rim. For the people who had driven it, and for many who had followed its journey from a distance, that silence was more than a technical end of mission. It was a reminder that Mars is not a backdrop for our stories. It is a real world with real weather, real hazards, and no obligation to keep our machines alive. Yet even as controllers sent a last series of calls and finally marked the mission as complete, the data Opportunity had gathered continued to reshape ideas about water, climate, and habitability on the Red Planet.
And out there on the same world that had just claimed a long-lived rover, another mission was quietly preparing to do something different. Not by rolling across the surface, but by listening to the planet itself breathe and shudder. That other mission was InSight, and from the beginning it was built on a very different idea of exploration. Instead of racing from crater to crater, it would land once on a flat plain and never move again. Its job was to feel the planet rather than look at it. You can think of it as a stethoscope pressed against Mars, listening for faint rumbles and distant thumps that would reveal what is happening deep inside. If you have ever watched a doctor listen to a heartbeat and infer so much from those tiny sounds, you already understand the gamble.
Could a single patient on a single patch of ground tell us how an entire world is built? To do that, InSight first had to survive a journey that is always more dangerous than it looks in animations. The spacecraft launched from Earth in 2018 on an Atlas rocket, coasted through space for months, then lined itself up for a fall toward a target called Elysium Planitia. Mission planners chose that location for a very boring reason. It was flat, low, and relatively rock-free. Perfect for solar panels, safe landings, and precision instrument placement. Terrible if you wanted scenic cliffs and dramatic valleys, but ideal if you wanted to hear tiny vibrations without being drowned in local noise. Entry into the Martian atmosphere followed the same unforgiving script that Opportunity had faced years earlier. A heat shield slammed into thin air at many thousands of kilometers per hour, converting speed into fire. A parachute deployed when the timing and pressure were just right. Retro rockets took over for the final stretch, guiding the lander down on its spider-like legs. Engineers like to call those minutes between atmospheric entry and touchdown the 7 minutes of terror, because there is no way to intervene once the sequence begins. Light takes too long to travel between Earth and Mars. By the time you know whether the parachute opened, the spacecraft has already either crashed or survived. InSight survived. It touched down gently on its 3 legs, unfolded its solar panels like wings, and began sending back the first pictures from a new home. Those early images showed exactly what planners had hoped for: a dusty, mostly featureless plain with only a few scattered rocks and gentle undulations. You might look at that scene and feel disappointed at how empty it appears. For the seismologists on the team, it was beautiful. A quiet, flat surface meant they could place their instruments carefully and trust that most of the vibrations they measured would come from deep within the planet rather than from nearby bumps and slopes. The heart of the mission was a sensitive seismometer called SEIS. Unlike a simple smartphone sensor that can pick up your footsteps, this device could feel motions smaller than the width of a hydrogen atom. But to work properly on Mars, it had to be placed directly on the ground, tucked away from wind and temperature swings as much as possible. This is where InSight differed from many landers before it. It carried a robotic arm with a claw and grapple, designed not to dig for samples, but to pick up the seismometer from the deck and set it down on the surface with exquisite care. That placement took weeks of planning and rehearsal. Engineers studied every nearby rock, every small slope, using stereo images to build 3-dimensional models.
They looked for a patch of ground smooth enough for a stable base and free of obstacles that might tilt or block contact. Commands were sent. The arm swung out, lifted the seismometer, rotated slowly, and lowered the instrument onto the soil. Once it was in place, the arm returned with a protective dome, a kind of wind and thermal shield, and gently covered the seismometer. From then on, SEs would listen in darkness, seeing the world only through motion. Alongside that stethoscope, InSight carried a thermometer with ambition. The heat flow and physical properties package, often called the mole, was designed to hammer itself several meters into the ground, pulling a ribbon of sensors behind it. The idea was simple to state and hard to execute.
If you can measure how fast heat flows from the interior toward the surface, you can work out how much energy is still trapped inside a planet and how quickly it is cooling. For Mars, that would be a direct window into the slowing heartbeat of its interior. Reality, as often happens on Mars, had other ideas. When the mole began to hammer, it did not sink as expected. Instead, it bounced, tilted, and sometimes even crept backward. The soil at Elysium Planitia turned out to have a surprising property. A tough crust of compacted particles sat over looser material. The mole had been designed with the assumption that nearby soil would press against its sides and provide friction, letting it move downward. Instead, that crust fractured in chunks, and the hole around the mole widened.
Without that lateral friction, each hammer blow only made the situation worse. What followed was one of the most creative troubleshooting efforts ever attempted on another planet. The team used InSight's arm and scoop as improvised tools. They pressed on the mole from above to increase friction. They pushed soil into the hole, trying to collapse it around the instrument so that each hammer stroke would have something to push against. They raked and dribbled sand with impossible patience, watching how grains behaved under weak gravity and thin air. For a while it seemed to work. The mole gained depth, only to stall again. Months turned into years of careful experimentation. Eventually, the team had to admit that the mole would not reach its intended depth. It had gone in far enough to collect some data, but not enough to deliver the clean measurement of heat flow that had been envisioned. In a way, this failure was itself a piece of science. Mars had once again surprised us by behaving differently from models. The near-surface soil had a strength and structure that were not anticipated. For engineers planning future drills and anchors, that knowledge is gold. For anyone hoping that this particular mission would reveal the planet's heat budget, it was a hard lesson in humility. While the mole struggled, the seismometer quietly excelled. Once it was insulated under its protective cover, SIS began to pick up signals from all over Mars. Some were local. Wind gusts rattled the lander and sent tremors through its feet. Temperature changes caused metal parts to creak and flex. The team learned to recognize and filter these surface noises, almost like learning to ignore the sound of your own breathing. Underneath that clatter, subtler patterns emerged. There were sharp, sudden jolts that looked like quakes. There were longer, ringing vibrations that hinted at waves bouncing through the crust and mantle. At first, detecting true Marsquakes was harder than many had expected. The planet is quieter than Earth. It has no bustling plate boundaries where slabs of crust dive and scrape against each other. Its atmosphere is thin, so storms, though dramatic from orbit, have less muscle in terms of ground shaking. Over time, though, SEI has accumulated a catalogue of events. Some were small, barely above background.
Others were large enough that scientists sat up in their chairs. The signature of these quakes carried information about where they originated and how they had travelled, like echoes in a vast auditorium telling you about the room's shape. In parallel, InSight's cameras and weather sensors kept close track of the environment at the landing site. Tiny dust devils sometimes marched across the plains, leaving faint tracks and brief jumps in pressure. The sky brightened and dimmed as atmospheric dust levels changed. Daytime temperatures rose to levels where electronics could operate comfortably. Nighttime temperatures plunged, forcing heaters to work hard to keep critical components within their survival range.
Each of these factors mattered because InSight lived on solar power with no wheels to reposition its panels once they were deployed. Dust is Mars's slow, patient predator. Grains settle on solar panels day after day, forming a thin film that blocks sunlight. On other missions, gusts of wind had occasionally provided cleaning events, sweeping panels clear and giving rovers like Opportunity fresh life. InSight did not benefit from such dramatic cleaning. The panels became steadily darker. To cope, mission controllers adjusted operations. They scheduled more activities during midday when power peaks, put the lander into safe modes during especially dusty periods, and gradually trimmed back instrument duty cycles to save energy. The team also tried something new. They used the robotic arm to trickle sand near the panels in carefully chosen spots. The hope was that these grains would bounce across the surface in the wind, colliding with dust particles and knocking them loose. In some cases, this did help. Small gains in power hinted that even on Mars you can sometimes sweep by throwing more dirt at a problem. But the effect was limited. No single maneuver could reverse years of accumulation. Through it all, the seismometer continued to deliver. It recorded quakes that originated near volcanic regions such as Cerberus Fossae, suggesting that some parts of the crust are still under stress. It felt the impacts of meteoroids slamming into Mars, events later matched with fresh craters seen by orbiting cameras.
By combining the timing and shape of different seismic waves, scientists began to draw a sketch of the planet's internal layering. The exact details of that sketch belong to the deeper analysis we will come to soon, but the broad picture was already clear. Mars is not a perfectly rigid, frozen billiard ball. It is a planet with a layered interior that still flexes and adjusts. There is a quiet drama in this kind of work that is easy to miss if you only look for spectacular images. A rover climbing a cliff or a helicopter taking off from alien ground gives you instant visual thrills. A line on a seismogram that shifts at a certain second, or a frequency that appears in a vibration spectrum, does not. Yet those wiggles are what turn the unknown into the known. They tell you how fast waves move through different materials. They tell you whether a core is liquid or solid, whether a crust is thick or thin, whether a mantle behaves more like stiff glass or slow-flowing honey. For the InSight team, each confirmed Marsquake was like finding a new key on a piano and pressing it to hear how the whole instrument responds. Some quakes had high-frequency, short-duration signatures that pointed to shallow, brittle failure in the crust. Others were more drawn out and rich in lower frequencies, hints that deeper structures were involved. By fitting models to these patterns, researchers chipped away at uncertainties in Mars's size, density distribution, and internal temperature. It is the kind of work where patience is everything. You wait for the planet to ring, then you listen with all the tools you have. As the mission aged, the tension between science and survival grew sharper. Every new sequence of observations cost energy. Every bit of energy spent meant less margin for the coldest nights and dustiest days. Controllers had to make hard choices about which instruments to run and when. They also had to accept that there would come a time when no amount of careful planning could keep the lander alive. Unlike nuclear-powered spacecraft, solar missions on Mars carry an invisible hourglass in the sky. That moment arrived in late 2022. Power levels dropped to the point where InSight could no longer guarantee both scientific operation and safe heating.
The team prepared for the end with the same care they had brought to the landing. They prioritized the most valuable final measurements, sent farewell commands, and then watched as signals grew weaker. Eventually the lander fell silent. Just as with Opportunity, calls went out for a while, hoping for an answer that never came. At last the mission was declared complete. The spacecraft remains there now, a still figure on a dusty plain, its panels coated, its instruments asleep. If you zoomed out at that moment and looked at Mars as a whole, you would see something striking. In one region, the tracks of a rover that had chased the story of water across plains and craters. In another, a stationary lander that had listened to the planet's interior for years. Elsewhere, orbiters circling overhead, mapping minerals, watching weather, and scouting landing sites. Each of these machines attack the same fundamental questions from different angles. How did Mars change from a warmer, wetter world to the frozen desert we see now? How much heat does it still carry inside? How long did it remain geologically and chemically active enough for life to have a chance? The raw facts of InSight's measurements are now stored in archives, but the process of turning them into understanding is still unfolding. When scientists sit down with those seismograms and try to fit models to them, they are, in a sense, still talking to the lander and to Mars itself.
The faint echoes of distant quakes and impacts are clues that can be combined with everything rovers and orbiters have found at the surface. Put together, they begin to reveal a three-dimensional portrait of a planet's hidden heart. The next step is to take that sketch and ask what it really tells us about a world that looks dead on the outside, yet still moves in slow motion within. When you strip away the romance, a seismometer is really in the business of timing. It waits for something to hit or crack, then measures how long different kinds of waves take to arrive. Some waves compress and expand the ground in the direction they travel, like sound moving through air. Others shear the ground side to side, more like the wobble that moves along a rope when you snap it. On Earth, we call the first ones primary waves and the second ones secondary waves, and the gap between their arrival times tells you what they pass through on the way. The beauty of this trick is that it works on any rocky planet. Primary waves can move through both solids and liquids, while secondary waves struggle in liquids and die out entirely in a molten core. By looking at which waves show up at InSight and which go missing, and by measuring how their speeds change with depth, scientists can turn a one-dimensional recording at a single point into a three-dimensional picture of interior layers. It sounds like a magic show, yet it rests on decades of physics tested on Earth. Mars became the latest patient on the examining table.
One of the first big surprises from InSight was the crust. Before the mission, models allowed for a fairly thin outer shell in some places, maybe a few tens of kilometers thick. The seismometer told a more complicated story. Signals suggested that under Elysium Planitia, the crust was thicker and more layered than many had expected, with possible distinct zones stacked on top of one another. That means Mars did not simply freeze its outer skin once and leave it alone. It built, reworked, and perhaps even partially melted and refroze that crust over long stretches of time. A thicker, more complex crust also helps explain why the surface of Mars keeps so much of its ancient record. On Earth, moving plates constantly swallow old seafloor and build new crust at ridges.
Mars seems to have followed a different path, one where the outer shell cooled, thickened, and locked into a more rigid state. Without wide-scale plate motion to recycle it, that shell preserves scars from the earliest epochs, including giant impact basins and old river valleys. When Opportunity rolled across those plains and looked into craters, it was reading pages that had never been torn out of the planetary book. Beneath that crust sits the mantle, the region of rock that on Earth flows slowly and drives volcanism and plate tectonics. InSight's data implied that Mars has a mantle too, but it behaves differently. The speeds of seismic waves moving through it and the way they bend and reflect reveal a material cooler and more rigid on average than Earth's mantle, yet not completely frozen. There are hints of warmer upwellings in certain regions, like a lingering ember under a log that otherwise looks cold. Those embers line up suspiciously well with volcanic provinces such as Tharsis, home to Olympus Mons and other giant volcanoes. That connection matters because Mars still shows signs of relatively recent volcanic and tectonic activity, especially near features like Cerberus fossae. Some Marsquakes detected by InSight appeared to originate there, suggesting that the crust is still adjusting under the weight and stress of ancient lava flows, or perhaps under the influence of deep mantle motions. You can think of Mars not as a dead rock, but as a slowing machine whose moving parts have not completely stopped. The mantle may no longer drive global plate recycling, yet it can still shift enough to crack the crust and feed occasional eruptions over geologic time. Deeper still lies the core, the hidden heart that once powered a global magnetic field. InSight's measurements, combined with earlier gravity and rotation data, point to a core that is large relative to the size of the planet and mostly liquid, rich in iron mixed with lighter elements like sulfur. The radius is big enough that the core takes up a large fraction of the planet's volume, more than many earlier models assumed.
A liquid core can slosh and convect, but the details of its composition and temperature determine whether that motion can sustain a magnetic field, the way Earth's core does. The consensus from the seismology is sobering. Mars likely had a vigorous magnetic dynamo early in its history, when the core was hotter and more actively convecting. At some point, as the planet radiated heat into space and the internal temperature gradient changed, that dynamo faltered and died. Without a magnetic shield to deflect charged particles from the sun, the upper atmosphere became vulnerable. Over hundreds of millions of years, solar wind stripped away lighter gases. The air thinned, surface pressure dropped, and liquid water on the surface became unstable over most of the planet.
Opportunity's ancient watery rocks and InSight's quiet, thin air are chapters from the same story, told from different angles. This thermal evolution is crucial for understanding the window of habitability. A planet like Mars starts with a budget of internal heat gained from its formation and from the decay of radioactive elements. That heat leaks out over time, carried by conduction and convection through the mantle and lost to space through the surface. If the planet is small, as Mars is compared to Earth, it cools faster. The crust thickens, mantle convection slows, and the core changes its behaviour. The timing of those shifts sets the length of time when you can have persistent volcanism, active cycling of gases, and surface water that is not locked away as ice. InSight gave us numbers for that cooling path, not just vague guesses. The pattern and frequencies of Marsquakes, the way waves rattled through the mantle and bounced off the core, all constrained models of how warm different layers must be today. Combine that with the known age of surface features, and you can estimate when the planet last had enough internal vigour to sustain a thick atmosphere and widespread liquid water. It becomes clear that Mars probably enjoyed its most Earth-like conditions very early, in the first billion years or so. After that, it entered a long decline, with the mantle and core slowly winding down. Meteor impacts recorded by InSight added another layer to this reconstruction.
When a space rock slams into Mars, it sends a burst of seismic energy outward and excavates a fresh crater. Orbiters can spot these new scars and match them to the timing of particular seismic events. That gives a ground truth test for the models used to locate and characterize quakes. It also reminds us that Mars is not only shaped from within, it is constantly being reshaped from without. Though today those impacts are smaller and rarer than the cataclysms that carved ancient basins. The quakes themselves came in different families. Some were high frequency and relatively small, likely associated with local cracking of brittle crust as it cooled or flexed. Others were lower frequency and more powerful, hinting at deeper sources. In a few remarkable cases, waves travelled through the core and back, giving especially strong constraints on its size and state. Each type of event illuminated a different depth range. Put together, they turned Mars into a kind of sampled sphere, where every jolt lit up a path into the interior like a tracer. For you and me trying to make sense of this, it helps to step back and see what kind of planet Mars turns out to be in the grand catalogue of possibilities. Earth is a tectonic world with moving plates and a long-lived magnetic shield. The Moon is a small, mostly solid body with a thick, cold crust and a core that barely stirs. Mars seems to sit between those extremes. It is more active than the Moon, with a warmer convecting mantle and a liquid core, but less active than Earth, with a static outer shell and a dynamo that died long ago. That in-between state has a name in planetary science, a stagnant lid planet, and it may be far more common than worlds like ours. That phrase stagnant lid can sound dull, but for the question of life it is anything but. If most rocky planets cool into this regime, where the surface becomes a thick, immobile shell over a slowly churning interior, then Mars becomes a crucial test case. It shows us how long such a planet can keep surface water, how quickly it loses its air once the shield goes down, and whether deep heat can still drive localized oases of activity. When you hear about strange seismic signals under Tharsis or quakes near Cerberus Fossae, you're hearing more than local news. You're hearing clues about what countless distant exoplanets might be doing right now. Insight also forced scientists to revisit an earlier assumption about layers. On Earth, we're used to thinking in terms of a crust, a mantle with upper and lower portions, and a core with solid and liquid zones. Mars appears to skip some of that complexity. Evidence suggests that its mantle does not have a distinct lower layer in the same way, and its core may lack a solid inner seed. That difference changes how heat moves and how the dynamo evolved. It is a reminder that even planets that look similar from a distance, both rocky and about half an astronomical unit apart in orbit, can take very different interior paths. All of this sounds abstract until you connect it to the images of dry river valleys, delta fans and lake beds carved on the surface. Those features tell you that water once flowed and pooled. The seismology tells you how long the planet could support the conditions that made that possible. Opportunity's sulfates and clay-rich rocks around Endeavour point to specific environments where water lingered and altered minerals. Insight's quakes and interior models tell you how the engine that powered that era ran down. Put the two stories together and you get a timeline where geology, climate and habitability rise and fall together. That timeline has one more crucial consequence. It hints at how deep you might have to dig, or how carefully you must search to find any lingering biosignatures. If Mars cooled quickly and lost its thick atmosphere early, then any surface life would have faced a harsh radiation environment for billions of years. Organic molecules near the top few centimeters of soil would be broken apart by cosmic rays and ultraviolet light. Any preserved traces of ancient microbes would likely be buried in rocks that were once underwater, or at least shielded, then later exhumed by erosion. That is exactly the sort of environment space agencies targeted when they chose the landing site for the next rover. Elysium Planitia and Meridiani Planum told us that Mars had water and that its interior cooled into a stagnant but still beating state. To test whether life actually arose during the window when conditions were best, you need a place that was not just wet, but biologically promising, with fine sediments capable of trapping and protecting delicate structures. You also need a machine sophisticated enough to select, drill and store samples so that laboratories back on Earth can one day search them grain by grain. The next mission in this chain was designed with that exact ambition, and it headed for the fossil-rich heart of an ancient lake bed called Jezero Crater. Jezero Crater had been on scientists' minds for years before any rover touched its floor. From orbit, it looked like a fossilized lake basin, with all the right features in one place. A clear inlet valley where water once flowed in, a smaller outlet channel where the water must have spilled back out, a fat triangle of layered sediments where a river had spread and slowed, dropping its load of mud in a classic delta fan. If you were hunting for ancient life, that fan was irresistible, because fine-grained mud can trap and protect delicate structures in a way that coarse sands and bare rock never can. The rover designed for this place was called Perseverance, and it was built with a very specific goal.
Not just to taste rocks and beam back data, but to physically collect and store samples for a future mission to retrieve. Its chassis and basic layout borrowed heavily from Curiosity, the earlier rover exploring Gale Crater, but almost everything else had been upgraded or redesigned. Cameras had higher resolution and wider ranges. Instruments could map chemistry and minerals with finer precision. The most radical addition was a complex system of drill bits, sample tubes, and caching assemblies tucked into its belly, like a geologist and a time capsule maker packed into one machine. Getting that machine to Mars followed the familiar arc of launch and cruise, but the tension never really leaves once a mission is underway. Months of flight give you time to check systems and refine your aim, yet they also give time for worry. Every valve, every sensor, every line of navigation software will have to work when the planet finally looms ahead. The landing site in Jezero had been chosen carefully, but it was also rougher than the plains picked for earlier rovers. Boulders, slopes, and the edge of the delta itself made it a high-reward, high-risk choice. That is why the descent was such a technological leap. When Perseverance hit the upper atmosphere, it rode inside a protective shell much like earlier landers, but this time the system carried new tools. Small thrusters adjusted its lift and angle as it plunged, allowing it to steer instead of simply falling on a fixed path.
A radar kept track of altitude and speed. Most importantly, a computer used terrain relative navigation, continually comparing camera images of the ground to an onboard map and deciding where it was safe to land in real time. All of that had to happen faster than any human could intervene. The famous 7 minutes of terror were really 7 minutes of precise choreography. Heat shield off at the right second, parachute out at exactly the right speed and altitude, backshell release and descent stage engines firing cleanly. A final hover as the sky crane lowered the rover on tethers and then cut itself loose to crash a safe distance away. From Earth, signals trickled in with an unavoidable delay. By the time Mission Control heard that the spacecraft had touched the top of the atmosphere, the rover was already either a smoking crater or sitting safely on its wheels. When the words indicating a successful touchdown finally appeared on screens, years of careful planning exhaled in one long breath. The first images were small and dusty, snapped through clear covers still smeared with landing grime. They showed exactly what scientists had hoped to see: a scatter of rocks, some angular, some rounded, sitting on a slightly sloping surface. In the distance, low ridges hinted at more complicated terrain. Before long, clearer panoramas arrived.
The team could pick out the broken cliff line of the delta front, the floor units they had mapped from orbit, and patches of terrain that looked surprisingly smooth and drivable. The rover had landed in a safe pocket, with a direct line of sight to the main scientific prize. Perseverance carried an arm as capable as Opportunity's, but with more advanced tools at the end. There was a camera system that could zoom and see textures almost at the grain level, a laser instrument that could vaporize a pinhead-sized spot on a rock and analyze the light given off to determine its elements. A pair of instruments mounted on the arm that, working together, could map chemistry and minerals at a scale fine enough to pick out tiny veins and nodules. There was even a small experiment called MOXIE, designed to pull carbon dioxide from the thin air and turn it into oxygen, a test of technology that might someday help human explorers breathe and fuel their rockets. But the most crucial hardware lived in the core sampling system. A hollow drill bit at the end of the arm could cut a cylinder of rock about as thick as a finger and a few centimetres long. That core would then be transferred through a complex choreography of motors and claws into a waiting sample tube inside the rover. The tube would be sealed, documented, and stored until the rover was ready to place it on the surface in a cache. Every step, from bite to seal, had to work perfectly, because these cores were intended not just for immediate study, but for a future journey back across interplanetary space. Before dashing toward the delta, the mission plan called for a careful campaign on the crater floor. Both the science team and the engineers wanted to characterize the rocks under the landing site and understand their origin. Were they sediments that had once formed the bottom of a lake? Were they volcanic lavas that had flooded in later and paved over older deposits? The difference mattered because it would set the starting point of the local timeline. The rover began by rolling to nearby targets, grinding away dusty coatings and taking close-up images of textures. The first attempt to core a rock was an unexpected lesson. The target looked solid and promising. The drill went in as planned, the system went through its motions, and everyone waited to see the result. When the tube was examined, it was empty. The rock had crumbled to powder during drilling, and much of that material had slipped away instead of packing neatly into the tube. No tube meant no sample for future return. It was a frustrating moment, but also a reminder that Mars does not read our manuals. In response, the team adjusted their strategy. They paid even closer attention to rock hardness and fracture patterns before choosing targets. The coring algorithm was tweaked to better handle fragile material. Soon enough, Perseverance succeeded in capturing a solid core from a more robust rock, later named Rochette. Images showed a neatly cut cylinder nestled inside the tube, a tiny beige log of Martian stone. For the first time, humanity had not just studied a Martian rock at a landing site, but prepared one to be shipped home someday. As the rover continued its crater floor campaign, evidence began to accumulate that much of the surface under its wheels was indeed volcanic in origin. Certain textures and mineral signatures pointed to cooled lava rather than sedimentary mud. That finding was not a disappointment. It meant that the crater floor preserved a record of igneous activity, which could be dated precisely if those rocks are ever analysed in laboratories on Earth.
Knowing the age of the floor would in turn anchor the timeline of the lake and delta sediments that lie above or against it. You can think of these early cores as anchor points in a story that will be filled in later. Each one carries not only minerals and textures, but a timestamp waiting to be read. When a future mission returns them and scientists measure the ratio of radioactive elements and their decay products, they will be able to say when that lava solidified or when those sediments were cemented. That will tell us whether the lake in Jezero was a brief episode or a long-lived feature, and how it fits with the broader history of Martian climate collapse. All through this, the rover was also running small technology experiments that hinted at how exploration might evolve.
MOXIE periodically gulped in Martian air and, through solid oxide electrolysis, split carbon dioxide into oxygen and carbon monoxide. Each successful run generated only enough oxygen to support a small dog for a short walk, but the principle was what mattered. If you can scale that process up, future missions could make their oxidizer and breathable air on site instead of hauling it all from Earth. Perseverance was not just reading the past, it was quietly testing tools for our future. The route planning also showed how different this era of Mars exploration had become. Earlier rovers relied heavily on human analysis of images to pick paths, with only limited help from onboard autonomy.
Perseverance could do more driving on its own, using a system that analysed the terrain in front of it and chose safe tracks within broad guidelines. That let the team aim for ambitious destinations without micromanaging every wheel turn. It also laid the groundwork for exploring rougher terrain near the delta front, where rocks and small cliffs could easily trap a less aware machine. Throughout these months, the delta loomed in the distance, layered cliffs several stories high, with subtle bands and cut surfaces, promised exactly the kind of fine sedimentary record that preserves traces of past environments. From orbit, scientists had already mapped channels within the fan where ancient rivers once shifted, cutting into their own deposits and leaving inverted ridges.
On the ground, those features resolved into more intricate shapes, with blocks and boulders perched in places that suggested powerful floods at some point in the past. Jezero's history was not a calm, unbroken lake. It had seen energetic episodes as well. When the rover finally began to approach the base of the delta front, it entered terrain that told a more complicated story. Some blocks embedded in the cliffs carried textures and minerals that looked more like rocks from far outside the crater. It appeared that material from the broader region had been washed into the basin and trapped, giving the rover a chance to study a much wider slice of Martian crust without leaving Jezero. In effect, the crater had acted as a natural collector, bringing distant rocks to one accessible place.
By now, multiple sample tubes held cores from the crater floor and from transitional rocks near the delta. Each one represented a bet that future scientists would be able to pull subtle signals from them. Perhaps the chemistry of certain minerals would show that water lingered for longer than models suggest. Perhaps microscopic structures in fine-grained layers would hint at biological activity, or at least at complex organic chemistry. Even if every tube turns out to hold only sterile stone, the detailed timeline they provide will tell us how quickly a potentially habitable world can lose that habitability. If you imagine standing next to Perseverance at the foot of those cliffs, looking up at the stacked layers of ancient mud now turned to rock, it is hard not to feel the stakes. Somewhere within those bands are seasons and centuries of a vanished lake. Each strip of sediment once lay at the bottom of a body of water under a thicker sky than the rover sees now. Dust storms raged above, rivers flowed in and out, ice may have advanced and retreated along the edges. If life ever took hold there, even at the simplest microbial level, this is where some echo of it might have been preserved. As the rover prepared to climb into the delta deposits and begin a more focused hunt for such echoes, another part of the mission was about to rewrite what we thought was possible in Martian exploration. Tucked under Perseverance before landing and then dropped onto the surface for a daring test, was a small, gangly machine with a rotor on top.
It had no drills, no spectrometers, and no sampling arm. What it did have was the ability to lift itself into the thin air and scout from above, turning the idea of a rover's slow crawl into something more like a partnership between ground and sky. The little helicopter was called Ingenuity, and on paper it was supposed to be a short-lived side experiment. It weighed about as much as a small house cat, had 4 spindly legs, and carried 2 counter-rotating blades that had to spin much faster than any helicopter on Earth just to bite into the thin Martian air. It rode to Mars strapped under Perseverance like a backpack, folded up behind a protective shield. The official plan was modest. Try a few short hops over the course of about 1 month, prove that powered flight in another world's atmosphere was even possible, then retire it and let the rover get on with its main job. Reality, once again, did not read the plan. Before Ingenuity could fly, it had to be lowered from the rover and survive on its own. Perseverance drove to a flat patch of ground, dropped a small debris shield, and went through a careful sequence to unfold the helicopter and set it on the surface. For a few days the rover lingered nearby, acting as a relay as Ingenuity tested its solar panel and electronics. Then, in an oddly emotional move for a machine, Perseverance drove away to a safe distance and turned its cameras back. It watched as Ingenuity spun up its rotors and rose into the air, becoming the first aircraft ever to fly on a planet other than Earth. That first flight was short, only a few tens of seconds, rising a few meters, hovering and landing. Yet the significance of what you were seeing in that dusty footage was enormous. A machine built on Earth had learned to ride a sky that was less than 1/100th as dense as our own sea-level air, using blades designed for that ghostly atmosphere and control software tuned for a gravity only about 1/3 of Earth's pull. The helicopter was fully autonomous during flight, making split-second adjustments that would be impossible to command from a distant control room. It was a proof that computers, sensors, and lightweight materials had finally reached a point where flight in that environment was more than a fantasy drawing. Once the first flight worked, the pace quickened. Ingenuity made a second hop, then a third, each a little more daring. It rose higher, flew farther from its takeoff point, and tested turns and sideways moves. Perseverance kept watch, capturing images from the ground, while the helicopter's own cameras looked down at the rippled surface. Soon it became clear that Ingenuity was not only surviving, it was thriving. Missions are often cautious about declaring success, but inside the operations team, you can imagine the shift in mood, from fingers crossed to what can we do with this new capability. The answer came quickly. Ingenuity began to scout ahead for the rover, flying over ridges and dunes to photograph terrain that Perseverance might later cross. From those images, the team could spot hazards such as deep sand traps or jagged rocks, and also identify promising outcrops before committing the rover to a route. A flight that lasted less than a minute could save days of cautious driving on the ground. It was as if Perseverance had gained a pair of eyes that could pop up and look around the next bend, then come back with a report. For you listening to this, it is worth pausing and imagining what it would feel like to ride along. You would see the rotor shadow flicker across the ground as you rise, the horizon dropping away, the rover shrinking to a bright point with its mast and wheels catching the sun. You would look down on your own tracks carved into the dust and notice details you could never see at eye level. Patterns in dune crests and rock scatter that hint at wind directions and past flows. Then you would come back down, the small insect of carbon fibre and aluminium, and hand that aerial memory to your bigger companion. Ingenuity's success forced a rethinking of its lifespan. Instead of shutting it down after the planned few flights, the team adopted it as a regular scout. It survived week after week, then month after month, flying whenever power and weather allowed. Each winter, as temperatures fell and sunlight weakened, the helicopter faced nights that pushed its batteries and electronics to their limits. Software updates from Earth tweaked how it managed heat and power, turning heaters off earlier to conserve energy, even if that meant risking colder components. It was a delicate balance between survival and functionality. At times, Ingenuity came close to the edge. Cold nights could drop its battery voltage low enough that its internal clock reset, confusing the schedule that kept it in sync with Perseverance. Dust on its solar panel cut into its ability to recharge. Engineers had to adjust operations, spacing flights farther apart and using the rover to listen for check-ins when the helicopter was expected to wake. In a sense, the two machines were learning to live with each other's quirks, like field partners in a harsh environment. Meanwhile, Perseverance was becoming a more independent explorer in its own right. Its navigation system could build three-dimensional maps of the terrain from stereo images and plan safe paths without human micromanagement. The rover set records for distance driven in a single Martian day, covering hundreds of meters by analyzing hazards on the fly. That autonomy freed the team to focus more on high-level goals, such as which layer of the delta to sample next, rather than worrying about every small rock in the rover's way. Some of Perseverance's tools gave it a kind of extra sense. Its laser instrument could fire short bursts of energy at a rock from a distance and read the glow given off by the vaporized spot, revealing the elements present.
From your perspective, it might look like a tiny science fiction heat ray flickering on and off, each shot turning a minuscule patch of stone into plasma for a moment. Its ground-penetrating radar sent pulses into the subsurface and listened for reflections, sketching hidden structure beneath the wheels. Combined with the helicopter's aerial view, the rover's world was a layered mix of surfaces and depths. Yet even with all this instrumentation, Mars still found ways to fool us. Images from Perseverance's cameras circulated widely online, and almost immediately people started spotting familiar shapes. There was a rock formation that looked like the opening of a doorway in a cliff. There were slabs that resembled broken machinery or the remnants of ancient walls.
A coil of string-like material appeared in one frame, which some viewers imagined as evidence of alien building, before mission engineers traced it to tangled remains from the rover's own hardware. Pieces of the landing system became characters in this story. The parachute that had slowed Perseverance's fall drifted downwind and draped itself over rocks, its bright fabric stark against the muted landscape. Parts of the protective backshell and associated debris scattered across the surface, some half buried, some perched awkwardly. When the rover and helicopter imaged these fragments, the result was uncanny. Here was proof of human presence, yet in forms that could easily be mistaken for something else if you did not know the context. NASA engineers were not content to just note their existence. They studied the distribution and condition of that debris to understand how the atmosphere had treated it during descent and how winds had moved it afterward. Every torn edge and scuff mark was a data point about supersonic airflow and material resilience. For the public, the same pictures became fodder for more imaginative narratives. Our eyes are hungry for stories, and Mars keeps handing us raw shapes on which to project them. This is where the partnership between our pattern-loving brains and our measurement-focused machines becomes tricky. When a camera sees a rock that happens to cast a shadow like a cat or a snake, the image is just pixels. It is the human who gives it whiskers and scales. When a laser scans a surface and finds a subtle change in chemistry across a tiny vein, That signal is easy to overlook in a quick glance, but can be deeply meaningful. If we want to be honest explorers, we have to learn to privilege the subtle but repeatable over the dramatic but standalone. The engineers and scientists on the Perseverance team live inside that tension every day. They know how tempting it is to chase visually striking features, and sometimes that instinct is correct. An unusual shape can mark an outcrop that has resisted erosion because it is made of different material. A balanced boulder can indicate past flooding or slope failures. At the same time, they know how easily a single, odd-looking rock can eat up valuable time without yielding much insight.
The rover's schedule is full, and every hour spent on one target is an hour not spent elsewhere. Ingenuity's aerial scouting helped balance that choice. By flying over an area and capturing a broader view, it could show how a strange feature fit into its surroundings. Was that block on a ridge part of a continuous layer, or was it an isolated chunk? Did the pattern seen from the ground extend for kilometers, hinting at a major deposit, or did they fade quickly? When you see the delta from above, those questions become much easier to answer. The helicopter essentially gave the team a way to zoom out before zooming in, and that perspective is a powerful antidote to being overly impressed by a single dramatic rock. As the mission wore on, Ingenuity continued to defy its original lifetime.
It flew dozens of times, then more than 60 times, travelling kilometres in total. It set records for speed and altitude in the thin air. Some flights hugged the ground to capture high-resolution images, while others climbed higher to map larger areas. With each new sortie, the risk grew. Motors and gears designed for a handful of flights kept spinning. Electronics endured cycle after cycle of cold and heat. The helicopter had no backup unit waiting in the wings if something broke. Eventually, the hazards caught up. One of its later flights ended with a harder-than-planned landing, and damage to its rotor blades meant that safe flight was no longer possible. When the decision came to end the helicopter's mission, it was less a failure and more a recognition that it had already delivered far beyond what had been asked. Ingenuity had changed how we think about exploring other planets. Future missions to Mars and elsewhere are already being designed with flying scouts in mind, and much of that design philosophy rests on lessons learned from this small pioneer. Perseverance, for its part, kept rolling. It climbed into the delta deposits, drilled more cores, and continued to test its own vision systems. Its autonomous driving software gained more experience in rugged terrain, learning how to interpret shadows and slopes in the harsh lighting of the Martian day. The rover's cameras captured more examples of rocks that happened to resemble familiar shapes, as well as more subtle layers and veins that held the real secrets. The human eye might still be drawn first to the cat-shaped stone, but years of work with these images have taught the team to look past the charm and focus on the patterns that match their models of water flow and sediment deposition. You can feel, under all this, a deeper psychological thread. We have sent a rolling laboratory and a flying scout to another world, and what do we do the moment the images reach us? We circle the rocks that look like animals. We zoom in on scraps of our own debris and talk about them as if they were relics in a museum. It is a very human reaction. We are social creatures, and we look for faces and stories everywhere we go. Mars is silent, so we supply the voices. Yet the most important things Perseverance is finding are not the ones that look like anything familiar at all. They are gradients in chemistry where certain elements quietly increase or decrease across a layer. They are textures too fine for casual viewing that show how mud settled in calm water or was later cracked by drying. They are the contents of small sealed tubes laid carefully on the ground, waiting for a mission that has not even launched yet. In those unassuming details, the question of life's presence or absence is being framed far more sharply than in any rock that resembles a door.
If you hold both halves of this story in your mind at once, the flights and the illusions, the scouting and the human tendency to see more than is really there, you begin to sense the real challenge. We are trying to detect something that may be subtle and rare using instruments built by pattern-seeking animals whose instincts were honed on a very different world. Perseverance and Ingenuity have shown that we can teach our machines to see in ways that complement rather than simply mirror our own vision. The next step is to ask what all of this seeing has really told us so far about Mars as a possible home for life, and what it implies about our place among the other worlds that circle distant stars. If you step back from all the mission patches and acronyms and look at Mars with a wider lens, a pattern starts to emerge. Opportunity showed that long ago parts of the planet held standing water, not just a splash here and there, but episodes of groundwater seeping through rocks and shallow basins where mineral-rich brines lingered. Insight showed that under the frozen surface there is still a layered interior with a warm liquid core and a mantle that has not completely gone to sleep. Perseverance is now threading the middle, collecting physical pieces of a time when a crater called Jezero held a lake and a river delta fed it with fine sediment. Together they sketch a world that was once much more alive with motion than it looks today.
The story those pieces tell is not a neat arc from blue planet to red desert. It is more like a series of overlapping windows that opened and closed on different timescales. Early on, when the core was hotter and the dynamo strong, Mars likely wore a global magnetic shield that deflected the worst of the solar wind. Under that shield, thick air could build, clouds could form, and liquid water could persist on the surface. River valleys carved their way into highlands, lakes filled impact basins. Volcanic provinces like Tharsis spewed gases that helped maintain the atmosphere. As internal heat leaked away and the core's motions changed, the magnetic field faltered. Once that happened, the solar wind had a clearer path to the upper atmosphere.
Lighter molecules were stripped away over hundreds of millions of years. Thick air thinned. Pressure at the surface dropped below the level where water is stable in the open for long periods. What had been a world with rain and lakes became a world where water retreated into the ground, into ice caps and into mineral structures. Opportunity's salty, acidic sediments at Meridiani and the clay-rich rocks at Endeavour's rim are local records of that broader transition. Insight's quakes and interior models add timing to this picture. They say that the engine which powered early volcanism and the dynamo is now running slowly, but not entirely stopped.
The mantle still moves enough to crack the crust, and perhaps feed occasional eruptions over geologic time, yet it no longer drives global plate tectonics. The core is still liquid, but the conditions that once made it a magnetic generator are gone. That means the generous window when Mars could have kept a thick, protective atmosphere was probably shorter than Earth's by a wide margin. Jezero Crater sits squarely in the middle of this drama. Its lake and river delta formed during the period when Mars still had enough water and air to support long-lived surface basins, but the system was already vulnerable. The sediments Perseverance is sampling do not come from a timeless, unchanging environment. Their layers record fluctuations in river flow, episodes of flooding, and perhaps periods when the lake shrank or even dried. Within that bustle, you can imagine countless small habitats forming and fading along shorelines and in shallow mud. Some would have been harsh, others more gentle, all of them guided by a climate that was quietly sliding toward thin, cold air. This is where the question, "Are we alone?" meets a more precise version. Was Mars once alive, even for a while? And if so, what killed that surface life? It is tempting to look for a single villain, a dramatic catastrophe that flipped the planet from habitable to hostile. The reality seems subtler and less forgiving. The planet was simply too small. Its heat reservoir was limited. Its dynamo could not be sustained indefinitely.
Without that shield, the atmosphere was slowly eroded. What looks like a sudden end in the geological record may have been the final stage of a very long fade. If life did emerge in that earlier, warmer era, its fate would have depended on how adaptable it was. Some forms might have died out when lakes froze and atmospheres thinned. Others might have retreated underground, following warmth and liquid water into pores and fractures. On Earth, we know microbes that thrive kilometers below the surface, feeding on chemical energy rather than sunlight. There is no obvious reason Mars could not host similar communities, insulated from radiation and temperature swings by rock.
In that sense, the surface we see today might be less a graveyard and more a cracked roof, above a still habitable basement. Perseverance will not dig kilometers down. It will not shine a flashlight into deep fractures. Its search for life is focused on fossils, on relics of past biology, preserved in fine-grained sediments, mineral veins, or concentrated chemical patterns. The cores it caches are bets that somewhere in those rocks, at the scale of tiny pores and laminae, there may be textures or molecules that cannot be explained by simple geology alone. Carbon-rich films in the right context, microscopic shapes in mineral matrices that match certain biological outlines, subtle imbalances in isotopes that suggest metabolic sorting.
If that proof exists, and if it can survive billions of years of burial and exposure, it will likely take the full power of Earth-based laboratories to tease it out. That is why the idea of sample return is so central. The plan, still unfolding as you hear this, is to send a follow-up mission that can land near Perseverance, collect some of the stored tubes, launch them into Mars orbit on a small rocket, and then hand them off to a spacecraft that can carry them home. It is an audacious relay race, involving multiple launches, precise rendezvous, and careful containment so that the samples arrive safely and are analysed under strict protocols. Imagine the moment when one of those tubes is finally opened in a clean lab on Earth.
Scientists will slice the core, polish surfaces, and examine them under microscopes with resolutions far beyond any camera we can reasonably fly. They will bombard them with beams of electrons and ions, read the distribution of elements and isotopes, and hunt for patterns that match the fingerprints of biology. Every promising texture will be checked against non-biological explanations. Every apparent biosignature will be tested with the assumption that nature can mimic life in many ways. If after all that, some features still defy geology and align with known biological processes, the implications will be enormous. One clear positive result would tell us that life can begin independently on at least 2 planets in the same star system, given roughly similar starting conditions.
That would be a strong hint that life is not rare, but a feature that emerges readily whenever there is liquid, water, energy, and time. In that case, the universe beyond our solar system is likely sprinkled with living worlds, some simple, some complex, some perhaps bearing their own curious creatures staring up at their skies. Mars would become our nearest example, the neighbour that confirms we're not a freak accident. On the other hand, a careful search that finds no convincing traces of past biology would not be a simple no. It would raise a different set of questions. Did life never start on Mars even though the conditions seemed right for a time? Did it start and then vanish without leaving obvious fossils? Are we looking in the wrong place, on the wrong scales, or with the wrong techniques? You might think of that outcome as the universe telling us that habitability does not guarantee habitation, that there is a difference between a planet where life could exist and one where it actually does. In that scenario, Earth might be more unusual than we like to imagine. Something about our particular mix of size, composition, orbit, and history may have allowed life not only to start but to persist through multiple global crises. The asteroid strikes, ice ages, and climate swings that punctuate our fossil record did not manage to extinguish biology entirely. They pushed it, redirected it, sometimes pruned it brutally, but the root remained.
If Mars, with its smaller size and faster cooling, failed to reach that same level of resilience, then it becomes a kind of warning. Being habitable for a while is not enough. A world has to maintain that habitability long enough for life to dig in. There is another possibility, one that sits uncomfortably between easy optimism and bleak pessimism. Mars might still host life today, but mostly in refuges we have not yet probed. If that is true, then the silence of the cores Perseverance collects does not reflect a lack of biology, but a limit of our reach.
To find present-day organisms, we would likely need to drill deeper, sample brines in buried aquifers, or explore environments like recurring slope lineae, those dark streaks that appear seasonally on certain slopes and may or may not involve liquid water. Such work pushes against technical, ethical, and planetary protection boundaries. You do not want to contaminate a world you're trying to study as a natural laboratory. Whichever outcome the Jezero samples eventually yield, Mars has already reshaped how we think about planets in general. The combination of Opportunity's long traverse, InSight's seismology, and Perseverance's detailed sampling has given us a template for reading a rocky world as a whole. You look at its rocks to see where and how water moved.
You listen to its quakes to learn how its interior cooled and shifted. You trace its ancient lakes and rivers to understand its climate history. Then you compare that integrated picture to what you see in the skies of exoplanets, where starlight gives you hints about atmospheres and orbits, but not yet close-up views of surfaces. When astronomers study super-Earths and mini-Neptunes around other stars, they often ask whether those worlds might be oceans from pole to pole, or dry and airless. Mars shows a third category that may be common: worlds that started wetter, lost their shields or heat more quickly, and ended up as deserts that still carry deep memories of their earlier, kinder days. On such planets, habitability is not a yes or no label. It is a curve that rises, peaks, and falls over time. If we want to know how likely it is that life exists elsewhere right now, we have to know how often that curve stays high long enough. For us, living on a planet whose core still drives a strong magnetic field and whose plates still shift, this has a quiet emotional weight. We tend to see Earth's current state as normal, yet in cosmic terms it is a phase, and not every planet gets to enjoy a phase like this for long. Mars is the reminder visible in our own sky that habitable conditions can narrow and close. When you watch its tiny red dot rise in the evening, you are seeing a world that may have been blue long before our own world ever saw a forest. The work ahead on Mars will not stop with Perseverance and sample return. Future missions may drill deeper, or send more capable landers to places like the mid-latitude ice-rich terrains. Human explorers may eventually set up habitats on its surface, not just as guests, but as long-term residents, bringing their own biology into a sterile landscape. If that happens, the line between native and imported life will blur, and the need to understand what was there before we arrived will become even more urgent. Our presence will become part of Mars's story, whether we are ready for that responsibility or not. For now, though, the quiet machines already there continue to define the frontier.
A silent rover resting on the rim of an ancient crater, a lander frozen on a plain that once echoed with Marsquakes, a working rover slowly building a cache of rocks that may carry answers across millions of kilometers. None of them can feel wonder or fear. That part is on us. We built them to ask in our place whether a small cooling planet next door ever knew life, and what that says about our chances among the stars. When the samples from Jezero finally arrive and are opened, the answer they give may be subtle, buried in graphs and microscope images rather than obvious headlines. Whatever that answer is, it will not belong to Mars alone. It will echo outward, into how we search other worlds, how we think about the fragility of our own, and how we imagine the universe beyond our familiar constellations. Until then, the red planet remains what it has always been in our sky, a steady, patient question mark glowing softly above the horizon, waiting for us to learn how to listen properly.